Hey, welcome back to the lecture. So in this lecture, we are going to learn about peripheral clock configuration. So we are going to understand how to enable a peripheral clock for a particular peripheral. So in most of the modern microcontrollers, before using any peripheral, you must enable its peripheral clock using peripheral clock registers. So by default, peripheral clocks of almost all peripherals will be disabled to save power. So as per the microcontroller design, whenever you start the microcontroller, the peripheral clocks will be disabled for almost all the peripherals of the microcontroller. So before you start working with any peripheral, you have to enable its peripheral clock. Peripheral won't take or respond to your configuration values until you enable its peripheral clock. And in STM32 microcontrollers, peripheral clocks are managed through RCC registers. So in STM32 microcontroller, there is a RCC peripheral. That is actually a system peripheral. Now that peripheral is used to manage clocks for various domains of the microcontroller. Let's understand this further by going through the reference manual of the microcontroller. I am in the reference manual here, and let's open the RCC section once again. So this is the RCC section. So as I said, RCC is an internal system related peripheral of the microcontroller, and this is majorly used for reset and clock control. By using the registers of the RCC, you can control clocks for various domains of the microcontroller like APB domain, AHB domain, memory domain, and for various other domains. RCC has various registers. Here it is. So you can click on RCC registers to explore its various registers, and by using these registers we actually configure the peripheral clock. Let's take an example. Let's say you want to configure the ADC peripheral. Let's go to the ADC peripheral first. I go to the ADC peripheral here. Here it is, ADC, and let's say ADC has its own registers. Let's click on ADC registers, and let's click on ADC control register CR1. And let's say I want to configure some bits in this register. Let's say I want to configure this bit 8. So I want to enable this bit, let's say. So we don't know what it does, but that's okay. This is just for the illustration. So in the ADC peripheral and in the ADC control register 1, we have to set the 8th bit, right? So let's make this bit as 1. Let's try this. So how do you do this? Very simple. So now you have to obtain the address of this register. So how do you calculate the address of this register? So here it is. They have given the offset. So add this offset to ADC register's base address, right? That's all you need to do. Let's see how this works. Let me go to the new project. So I have created a project, peripheral clock enable here. Let me first write a macro for ADC base address. So what's the ADC base address? So you have to understand this by going through the memory map, isn't it? Let's go to the memory map. And here, just search for ADC. So here it is. So ADC you can find on APB 2 bus, isn't it? So this is the base address of the ADC registers. Let's copy that and let's go to the program and let's paste here. So this is the base address, right? So now let me write unsigned long. UL stands for unsigned long, right? Because address is always unsigned, isn't it? And what is the offset of the register? Hash define ADC CR1 reg, right? CR1 register offset. So what is offset? We know that offset is 0x04. So offset is always mentioned along with the register. For example, if you go to the ADC CR1 register, offset is mentioned here, 04. So you just have to add this number to this number. You just have to add 04 to this base address to get the peripheral address of ADC control register 1. So now let me create one more macro, ADC CR1 reg address. This is nothing but base address plus this offset, right? Great. So you can also use UL here. Fine. So now let's create one pointer variable u in 32_t. Let me call it as PADC CR1 reg. So let me equate this pointer variable to this address. So I cannot do like this. So I have to typecast this to uint32_t star, right? So since I'm using a type dep notation for the data type, I have to use include std in.h. So I just created a pointer variable and I initialized this pointer variable to this address. And now let's use this pointer variable to program the 8th bit of this register. Let's make it 1. Star PADC control1 reg or is equal to 1 shifted by 8, isn't it? So by making this, we actually set the 8th bit of that register, isn't it? Let's compile and execute on the board. Now let's see what happens. So you can see that this doesn't have any errors. So now let me connect my board and let me debug this. And let's single step. I'm doing stepping over. So let's check the SFR. Window show view SFR. Let's check the ADC register. Let's go to ADC1 and let's go to CR1 and here it is, the scan bit. That's the 8th bit and it is not set. Why is that? So you actually dereferenced its address here and you actually wrote the value 1 into the 8th position, right? But the peripheral didn't take that. The reason for that is the clock for that peripheral is not enabled. So that's the reason before you configure any peripheral register of any peripheral, you must enable its peripheral clock first. Otherwise, it won't take your configuration value. So that's the first lesson you should learn while configuring different peripherals. So make sure that its peripheral clock is enabled. Let's understand how to enable the peripheral clock of this peripheral. The peripheral in question is ADC. Now, before enabling a peripheral clock for a peripheral, first you must understand on which bus it is connected. So that information you can obtain from the reference manual itself. Let's go to the reference manual and let's go to the memory map, right? So here, if I just search for ADC1, so it says that ADC1 is actually connected to the APB2 bus. So you can even cross-verify this using the datasheet diagram. Let's go to the datasheet. And if I go to the data sheet and I open this architecture diagram, so here is an architecture diagram, isn't it, or block diagram. And yes, it is, the ADC is indeed connected to the APB2 bus, isn't it? So that's the first thing what you have to do. First, obtain the information about its bus, a parent bus. In this case, the parent bus is APB2. And after that, go to the RCC registers to search for the appropriate register. Let me go to the RCC register, right? And here in the RCC registers, you have to refer to the peripheral clock enabled registers. There are many peripheral clock enabled registers. For example, this is RCC AHB1 peripheral clock enabled register. This is for AHB2 bus. This is for AHB3 bus. This is for APB1 bus. And in our case, it must be APB2, isn't it? Since our peripheral is connected to APB2 bus, we should be referring to this register, RCC APB2 peripheral clock enabled register. That makes sense, isn't it? Right? Suppose if you are using, let's say, GPIO-A, GPIO peripheral. In that case, GPIO is connected to AHB1 bus. So you must be referring to AHB1 ENR. This one. So now I'm going to APB2 here. So we should be referring to the RCC APB2 ENR and its offset is this one from the base address of the RCC registers. And here it is. You have to set 8th bit of this register to enable the clock for the ADC1 peripheral. Right. So here it is. The description of bit 8 ADC1 clock enable. So by default it is 0. You can see the reset value, it is 0. So that means all the APB2 peripherals are disabled by default, right? So now let's do this. Enable the 8th bit of the RCC APB2 ENR. Let's go back to the IDE. So here, let's create some more macros. Define RCC base address. And after that, let me create one more macro, RCC APB2 ENR offset. And after that, let me create one more macro, RCC APB2 ENR ADDR. So what's the RCC base address? First, let's solve for RCC base address. Let me go to the reference manual. Let's go to the memory map, and here let's search for RCC. Here it is. Base address is this one. Let's copy that and let me make it as an unsigned long number. And after that, what is the offset of APB2 ENR? We just saw that, right? 0 cross 44. And after that, sorry, here define RCC APB2 ENR address. So it must be RCC base address plus APB2 ENR offset, right? That's it. And now before doing this, let's enable the clock. First, enable the peripheral clock for ADC1. So here let me create one more pointer variable. Let me call it as PRCC APB2 ENR is equal to, let me use the same code here. So let me use this macro here. And after that, here let's dereference that pointer. We have to set the 8th bit, isn't it? So 1 shifted by 8, right? And after that, step 2 is modify the ADC CR1 register. So prior to that, clock must be enabled using RCC register for the ADC. So that's the meaning of this code. Let's recheck our code. So now let me just step over, right? So here the clock is enabled. Let's verify that. In the SFR section, go to RCC and go to APB2 ENR. Here it is. Let's open that, and here it is. Clock for ADC1 is enabled, isn't it? It is showing 1. And now let's single step. So now check the ADC control 1 register. Let's go to the ADC control 1 and scan. Here it is. It is now set to 1, isn't it? So that proves that without enabling the peripheral clock, the peripheral won't take your configuration. So apply this logic or technique to any peripheral you have in your mind. It doesn't matter whether it is ADC or SPI or I2C timer. It doesn't matter. So these points actually apply to almost all the peripherals of the microcontroller. So now when we do our driver development task in the future lectures, so you would need all this knowledge, and you will see more examples as you make a progress. And with that note, I would like to end this lecture, and I will see you in the next lecture.